Welcome to this ANSYS Workbench tutorial on buckling analysis of column. We are going to use ANSYS 2023 student model to simulate the buckling of a column. Before getting into the detailed analysis, let us understand what is exactly a buckling load. It is a critical load at which the column becomes unstable under compressive stress. So, when a column is subjected to this load, which becomes unstable because the deformation which is caused in the column is severe. So the structure loses its stability. So while designing a column, one must have a good understanding on buckling load. Now let me read the problem. Determine the buckling load of a solid round steel column 3 meter long and 5 centimeter in diameter using finite element analysis and analytical methods when the two ends of the columns are hinged. So the boundary condition is the two ends of the column must be hinged. Okay. For this condition, we have to identify what is the crippling load or the buckling load at which the column loses its stability. Now let us see how to perform buckling analysis using ANSYS Workbench. So I have opened the ANSYS Workbench model. Here you see unsaved project. So I am going to save the project by giving the name for that. It is a buckling analysis. So I am going to give that name as buckling analysis of column. Now you can see that the name of the analysis is changed into buckling analysis of column. So in this analysis, we are going to perform two analysis subsequently. The first one is static structural analysis. So I am going to select the static structural analysis. You can double click on that so that it will be made available in the project schematic, or otherwise you can select it and drag it all the way to this project schematic. So in either way, you can select the particular toolbox from the ANSYS Workbench model. Either you can double click or otherwise you can select it and drag it on that particular project schematic. So in this workflow, we have engineering data, geometry, model, setup, solution, results. So we have to begin with engineering data. Here we have to define the material property. So structural steel is a default material in the ANSYS Workbench. We are using the same material for modeling the column. For verifying its properties, we can move down here and you can check out the density of the material, which is 7850 kilogram per meter cube. And you can also check the isotropic elastic properties. That is the Young's modulus of the material, that is 2 multiplied by 10 to the power 11 Pascal, or we can say it as a Newton per meter square. Poisson's ratio is 0.3. So everything is already set and which is found to be correct. So we don't want to do anything on that. If you want to create a new material, then you can click this portion to create a new material and we can set new properties for the particular material. So for this analysis, we don't want to create a new material. We're going to use the structural steel. So we can close this engineering data. And now we are going to create a geometry. So we're going to create a column by using a CAD modeling model which is available in the ANSYS Workbench. So there are two models. One is space claim, another one is design modeler. So if you go over the geometry, you right click on that, then you can see that this pull down menu. Here you can see that space claim and design modeler. So we're going to use design modeler for creating geometry. So I'm selecting this design modeler. Now here you see the display starting design modeler. So now the design modeler is ready for creating a geometry. In this tree outline, first we have to select the plane on which we are going to make the drawing. So I'm going to select ZX plane. So ZX plane. So now the coordinates are visible in the window. So on which I'm going to make a sketch. So the moment I click on the sketch, here you see number of sketching features which are available in the design modeler, starting from line to circle. I'm going to make a circle because I want to make a circular column. So to select the circle, and about this point I am going to create the circle on this ZX plane. So to get a clear view on the particular region, I am going to zoom this particular region alone to get a clear view on that. Okay, and then I'm going to draw the circle. Okay, then we have to deselect the particular zoom option, and then I'm going to click on the circle, going to create a geometry. So now we have constructed the circular geometry here, and then we have to define the dimensions for that. So for that, here in this menu, the option dimension is available. You have to click on that, then you can see the different option for giving dimension. We are going to give the diameter for that feature. So diameter is defined. So we have to change the value into the diameter of the column, which is 0.05 meter. Okay, so now here you see the circular feature is created, and I'm going to extrude this feature. So by clicking this option extrude, I want to select this particular geometry, and I'm going to apply that. Okay, so then we have to define the depth of the extrusion. So here I'm going to give 3 meter, which is the height of the particular column which is provided for analysis. So we have given the height is 3 meter. Okay, we have extruded the feature. So here it is a zoom to fit option. You can see the column which we have drawn on this ZX plane. So now we have constructed the geometry. So we can close the design modeler. You see here the tick mark because the geometry is updated in the workflow. So now we are going to carry out meshing by discretizing the model. So I double click on that model option. So here you see starting mechanical. So now you can see that the entire model is imported into this, and geometry, material, all the things are imported into this model. So first we are going to carry out meshing. So I'm going to right click on that, then insert sizing. Okay, I'm going to control the size of the machine. So I'm going to enable this option sizing. So for that you have to right click on that, then you have to select sizing. So the moment it is enabled, here you can see that geometry selection. You have to select the entire geometry for that. So I'm going to enable this body selection. So I can click on the entire object. So the entire body is selected, apply. So the body sizing is applied for the entire column. So we have to define the size of the element. So it is the minimum element size which is used for discretization of this column. So I'm going to give 0.01 meter for the least element size. So after giving this value, I'm going to create a mesh by right clicking on the mesh option, and then I'm going to give generate mesh. Now we can see that the mesh is created, and if you want to check out the statistics, you can go for verifying this number of nodes and elements which are created after discretizing the entire body. So after creating a detailed mesh, we are going to give the boundary conditions. So we know that there are 2 points. One is the top of the column and another one is the bottom of the column. On top, both the ends are hinged. So let us take this point as A and the bottom point as B. At A, we have to give the displacement constraint. So how to give it? Right click on the static structural, insert displacement. So now you can see that the menu which indicates we have to select the geometry on which we are going to give the displacement constraint. So for that, I'm going to zoom the particular region where we have to apply the boundary condition. So this is the region where we have to apply the boundary condition, that is the displacement constraint. So I'm going to select this particular face and apply. So at this point, I'm going to give the x displacement as 0 and y as free and z as 0. The reason for giving y displacement as free means the column is subjected to compressive load. So by giving the displacement as free, we can give the compressive load on the particular face, or otherwise we cannot give that particular load. So we have to give the displacement as free for y axis. Okay, for other 2 axes we have to give 0. So now the displacement constraint is defined at the top face of the particular column. Now we are going to give the loading condition. For that, again we have to select the static structural and then right click, insert, then force. So here you can see the force is there. I'm going to apply the force on this face. Again, we have to select the face, apply, and the magnitude is 1 Newton. So it is the reference compressive load. We will see the importance of this at the end of the analysis. I'm going to give that value as 1 Newton. So we have to define the direction of the load. For that, here option is there, direction. If you click on that, then it allows us to change the direction of the force. So it has to be like this because it is a compressive force. So I'm going to apply it after changing the direction. Now at point A, we have defined the displacement constraint as well as loading condition. Now let us move on to the bottom end of the column, where also we are going to define the displacement constraint. So to see the bottom of that column, we are going to pan it around so that we can get a clear view of the bottom surface. So then I'm going to rotate this object so that I can get a clear view on the bottom face. This is the reference B where we have to apply the displacement constraint. So as we need to apply rotational constraint on this face, we cannot give the displacement constraint. So we have to give a remote displacement constraint, because here you see it allows us to give rotational constraint along with the displacement constraint. So I'm going to select the remote displacement option. So here also we have to select the geometry. So click on this face. I have selected this. So apply. So this face is selected. It will ask for 3 information. One is coordinate system. So we are going to give 0 along x coordinate. Y coordinate is also 0. Z coordinate is also 0. So here you see the location is 0, 0, 0 meter. And then it asks for displacement constraint. The displacement along x component is taken as 0 and y component is also considered as 0 and z component is also considered as 0. As far as rotation is concerned, along x-axis it is free and along y-axis it is considered as 0 and along z-axis again it is considered as free. So here you see the rotational constraint. Free along X direction, 0 along Y direction, and free along Z direction. Now the displacement constraint is also set for the bottom end of the column. So after defining the loading as well as boundary condition, by clicking on the solution, we are going to insert the deformation, that is total deformation. Okay. Then we are going to solve the entire analysis by right clicking on the solution and then by clicking solve. So now you see the solver is developing mathematical model and solving the problem. So now we can see that the static structural analysis is completed. So once it is over, we are going to close this model and you see the tick marks in all the workflow starting from engineering data to the results. Now we are going to conduct the eigenvalue buckling analysis. So we are going to insert this toolbox right into the static structure. How to do that? We're going to select it and by using mouse you are going to drag it all the way to this project schematic and we are going to leave it after selecting solution of the static structural. On top of that I am going to leave it. So the solution of the static structural analysis is carried to the eigenvalue buckling analysis. Here you can see there is an interface between static structural to the eigenvalue buckling. Engineering data, geometry, model as well as the solution. So now I am going to set up the eigenvalue buckling analysis. So here I am going to double click on this setup. Here you see starting mechanical. It indicates that it is working on that. So here you can see the eigenvalue buckling analysis model and make sure the tick mark in the pre-stress condition, and on analysis setting by default number of modes to be extracted is given as 2. You can give 10 if you want to have a better understanding on mode shapes, or otherwise 2 is sufficient. So I have selected 10 modes here in the analysis settings. Then in solution menu I am going to click on insert and deformation, total deformation. Okay. So now I am going to solve that eigenvalue buckling analysis. So now you can see that the solution is done. We can see the load multiplier. So this value gives us an idea about the buckling load of the column. So as we want to extract 10 modes, so here you can see the load multiplier value for the 10 nodes. So if you want to determine the deformation for all these modes, you can select all those things and right click, create mode shape results, and here you can see the mode shape results for the all the 10 different modes. So now you can see that the total deformation for various mode shapes. Now let us animate this. So I'm going to select 10 seconds and here 100 frames to see how it looks like. Okay. So for us, the first two modes are sufficient. These two gives almost the same value, that is 67,191. So now we found that the load multiplier value is 67,191. So but it does not exactly reflect the crippling or buckling load of a column. So how to find out the exact value? We have to find out the buckling load by multiplying this value, that is the reference value what we have taken for the static structural analysis, that is 1 Newton, with the load multiplier. So this value will give the exact buckling load of a column. So the question will eventually arise whether the reference value will impact the buckling load of the column. Absolutely not. So if I take the 2 Newton as a reference value, then the load multiplier value will be exactly half of this value. So no matter whatever the value that we take for this reference value, this buckling load will not change. So in this analysis, I told you that we are going to verify the results analytically. So we are going to use the analytical approach to find out the buckling load. So the diameter of the column is 0.05 meter and length is 3 meter. We are going to use the Euler's column theory, which gives us the buckling load as pi square EI divided by LE square. Here the equivalent length is exactly the same as that of the length of the column, since both ends of the column are hinged. So we are going to calculate by substituting Young's modulus and moment of inertia value here. We can find out the buckling load. So after substituting these value, we got the value of buckling load as 67,288 Newton, which is almost closer to this value which we have obtained from the ANSYS, because the error is less than 1%. So if you calculate the error between this analytical and the finite element results. Okay. So from that, we can also verify the ANSYS results with the analytical results. Thanks for watching the tutorial.